discussed it with Recursion Pharma. You heard of him?
No.
That's where he works.
Even though I think he worked at the Gateway place with that pharmaceutical company.
Recursion Pharma.
Oh, they said something else.
That was with all your copies.
Oh, nice.
But now I'm trying it.
So is there a Canvas place for this course?
A canvas what?
Just a Canvas
Canvas.
for him?
There are like some papers that don't like.
You guys code anything, or is it also theory?
So I have.
Now we do Google Colab, Collaboratory. So we just write everything in Python.
Yeah. Yeah, why not? I was talking to Carnivore because I was like, oh, what am I doing? But I guess while I was talking to him, I realized like, oh, the L2 locks and the L1 locks would actually be the same in this setting because they're conventional things anyway. And he was like, yeah, the L2 locks might have. He was like, I was thinking the L2 locks just because there might be some weird customer. He's like, no one uses L1 locks, so there might be like weird, like weird inputs or something.
Oh.
Which I don't know if it's actually true or not. But they are the same thing as this dimension. So let's try it again. But then I also wanted we looked at a loss function deals with almost L1. Raise things to the alpha.
Yeah, good.
Right.
If you don't mind, I hooked up to.
Yeah, that's great.
I got a few slides. In fact, same kind of slide this year.
Okay. Yeah. Take 5 minutes of break.
That'll be good. Yeah. Just let me know when you want to start.
You can start. End of the semester.
About what? Oh, I didn't.
We have 16 minutes.
Okay.
So we assigned everybody 3 minutes.
I've already got some asking how to work.
I mean, it'll be recorded now, but we'll have to watch out.
Yeah.
Yeah, we have a Canvas thing. Can you,
Sure.
You better have to put your email out.
No, I'll almost certainly forget, so I do just.
I'll just say, yeah, no problem.
Yeah.
Okay, we're going to get started. I'd like to introduce Tom Henderson, who is going to just briefly introduce to you all a new certificate that the university is offering on deep learning. And yeah, I saw a presentation on this the other day. It looks awesome. And yeah, she's going to just briefly let you know about the opportunity in case any of you are interested. And then we'll get started with the lectures. So I think, yeah, I know. So I do the same thing every class.
Is there anything to that?
That's no, you can do like this one.
I'm trying to get rid of these.
Do this one.
I tried all of it.
No, this one, and then turn off.
Oh, there you go. Okay, thanks. All right, well, thank you very much. Yeah, I'm just going to 4 or 5 minutes talking about this. So there's been, the state got interested in deep technology, whatever that meant. So they asked for proposals on ways to work with industry and programs that are of interest to both university and industry, related to jobs as well. So we put together a deep learning and AI and robotics proposal. It's got me and some people from civil who does a lot of logistics for transportation, some electrical engineers who do image processing, and then there's companies involved. And so just to show you quickly, so Bert's been part of this as well, and some others in School of Computing who do various kinds of stuff, including robotics, image processing, deep learning, and then he does language processing. And then in civil, there's a number of people who do, like I said, this kind of stuff. So what is it all about? The idea is we're going to offer a certificate which is stackable on top of whatever degree you're going to get as a grad. So you would get the certificate in addition, and it would certify, in some sense, that you've covered this material and have done a couple things. One is get some working knowledge of this area. The other is to do a kind of capstone project, 3-hour course where we work with industry to give us some stuff. You have a faculty advisor, you work together as a team to figure out some solution to a particular problem that's been posed. Or even just looking at how you get at such a solution. So the working knowledge means these are some courses in SOC, so computer science, specific courses. You take one or more of these, one or more of these. This includes also some civil engineering courses. And then a course in deep learning, that's this course. So that's a required course. The others you have a choice. And then that's sort of the courses you take. And then a 3-hour capstone project internship course where you work on a project with a team and a faculty member related to some industry. Why is the state interested? Well, we looked at just Indeed or something, and there's about 1,000 jobs listed in this area in Utah where they'd like to hire people. So they're very interested in that. Moreover, this whole area is supposed to grow. It's the biggest of any area offering employment in the U.S. in the next 10 years. So it's a big area. So you take at least one course out of that. Those are about 3 hours each. At least one out of that. This one's required. It's 3 hours. This one's required. We hope to offer this next spring. So we're going to try to offer a first run of this in the spring, where we'll figure out what's going on and what kind of projects we're able to do. And we're trying to get certified so that we can have certificates available at the end of spring. So if somebody does that course, they've done the others, then they can have a certificate. So the idea is that you would then have credentials to show industry, and you'd have experience and knowledge, and you would have worked on some problem in industry. So who's working with us? Well, NVIDIA is providing support for the training and teaching and use of this stuff. Blency, this company, a local company that does a lot of IoT, is very interested in their, actually going to host, we're going to buy a big GPU system. Blency does a lot of IoT, and I'll talk about that, because it's kind of weird stuff, maybe you never think of a lot of it. We have worked with Kairos Autonomy. I worked on the DARPA Urban Challenge, which is an autonomous vehicle program, and they provided key components for us. We also work with UDOT, Department of Transportation. I'll show an application where they and Blency got together on something very interesting. And we work with sort of DoD people as well. These guys analyze a lot of data, and they're interested in this kind of thing as well. So here's a simple example. So a few weeks ago, turns out my student works on some of this stuff, and the state, UDOT, asked Blency, where he works, they asked him, we have these traffic barrels, and we have people put them out there, and they put them somewhere, but they really don't remember where, and they didn't put them where we said to. How can we find our barrels? So it turns out there are companies that collect dash cam images. They pay people to take pictures as they drive around. They collect millions of images. So he did a very quick project, 2 or 3 days is what he, I think, where he transferred a learning to find these barrels in images, and within a week or so, Blency had a product. They'll tell you where all your barrels are. Right? It's got the GPS with the image, so they can tell you where these are. So other states are very interested in this. This is the kind of thing that got their attention. That, wow, this could do some good stuff. What else can you do? So we're also working on unmanned aircraft systems. So this is a proposed, I worked on this set of airways over Salt Lake City, over the East Bench. And we're hoping to have thousands of flights where we coordinate all this activity going on above where they don't run into each other. It's another area of such a thing. If you're working someplace and you're interested in this, well, it could be that maybe your company would want to partner with us. We can work on some problem with theirs. If you have questions, you can contact me. The program is not yet, it's going through the approval process, so until then, you can ask me about it, I can tell you a lot more about it. The idea is that this should be fun and interesting and do us all some good. I'll quit there. So if you have questions, you can send it to me. I'm in the School of Computing, so my email and all that stuff is also there.
Great. Thank you, Tom.
Thank you for giving me the time.
By a strange set of coincidences, Tom's son-in-law was also did a PhD in math here at the same time that I did, and is a friend of mine. So anyway,
With the same advisor, right?
with the exact same advisor. Yeah. So anyway, good to see you. Thanks for coming through that. All right, I'm gonna kind of just quickly get set up here so we can get going on the lecture. Any questions? I last night finished up all of the first passes on the final project proposals. So everybody got some kind of feedback on that. At the same time, I realized that I had made a mistake and not made it a group assignment. So you hopefully got the announcement where I mentioned, there's actually now another assignment that I'm asking you to just re-upload your proposal to, since I can't do that very easily from within Canvas. And that's where all the feedback and scores will go there. So a lot of you have already uploaded your assignments. Thank you, or your proposals. Thank you very much. And yeah, so we'll communicate over Canvas on back and forth on the comments that I made. So for some of you, it was like, great, just get going. Others, there were some questions that I would like to have answered first by you before approval. I think in one or two cases there was like, this is probably too ambitious or like not ambitious enough. So anyways, just let's make sure we get the right, that we get to the right spot, and then you get approved. You'll know you're approved and you get that point saying that like, hey, well, I'll say it's approved, and you also get a point for that. Any questions on that? Yeah.
So how would you have created groups if you didn't have the proposal first?
I have no idea what you're asking.
I mean, you said you recreated a bunch of groups and then created an assignment for that.
Right.
How would you have known what our groups were?
Well, Canvas allows you to create the groups as you turn it in.
Oh.
But since I already knew what they were from the proposals, I just made them. So yeah. So that's how I was supposed to have done it. I didn't do that. The nice thing about using group assignments is like when I give a point, or when I give feedback, everybody in the group gets the feedback. When I give a point, everybody in the group gets the point. Right. And plus, then we use the same groups for the final project. All right. Any other questions before we get started? Okay. Well, let's get going then. So, the plan for today is we're going to recap GANs. They're very different from what we've done before, so I want to have a chance to kind of talk about them a little bit more, just to kind of review what we did last time, look at a little more of the applications of them, and then briefly talk about a way of combining GANs and VAEs, and then we're going to get into something called contrastive learning, or metric learning, it's sometimes called, and then what's called self-supervised contrastive learning, which is a fairly new way of trying to get state-of-the-art performance in terms of, like, for instance, classifying objects in an ImageNet, but without using the labels at all, which is quite interesting. And this is like, for some groups like Facebook AI, they're very interested in these kinds of things, and pushing a lot of the research there. Okay, so recap of GANs. Remember this whole story. Real data, samples from some distribution. The generator turns that into what should be eventually, looking like a sample from our training data. Discriminator is the agent that's trying to decide. It's a supervised binary classifier trying to decide, which is real data, which is fake data, and we use the signal from the discriminator to train the generator. And this is how the generator can get quite good, quite good, like produce, in the case of images, like, very high resolution images, is that it uses this adaptive kind of scorer, this discriminator, that, hand in hand, they're working against each other, but actually become quite, good together as a result. We don't have tons of time because we had that before, so I'll skip through that goofy cartoon. Yeah, it's just kind of saying the same thing. Remember, this is what we looked at this a bunch yesterday. This is the Minimax objective function. We're maximizing this objective function over the parameters of the discriminator, and we're minimizing it over the parameters of the generator. And the way that we do this is to alternate between taking gradient descent steps with respect to the discriminator's parameters, and then taking gradient descent steps with respect to the generator parameters. We saw that actually, with this formulation, it tends to be the case that there's a poor signal, poor gradient signal, where we need there to be a better, where we want there to be more signal, so we swap out that the gradient descent steps in the generator and actually turn them into gradient descent steps by just having, instead of this being a 1 minus d, just being a log d. So that switches this objective so that we have lots of gradient signal, typically where we are trying to distinguish these things the most, where we're assigning 0 to the generator, to generating images, which is going to be doing that. Okay, questions so far? Let's just review. Anybody still what the heck's going on here? Everyone did it.
I guess I have a question.
Yeah.
Maybe it's more of a philosophical question. What is the purpose of trying to get it to generate these nice images?
Why would you want a generator?
Why would we want to do something like this?
Yeah. So yeah, what's the use of that? I guess what applications are there? We're going to go through some slides that will have applications on them, but in general, this is the basic question is, can you learn to sample from a very complex? So the basic generative question is, can you learn the data likelihood function, the p of your data? Can you learn that at all? And if you have that, you can do really cool things, right? Like you can give the likelihood function an image, and you could it can tell you if it cites high probability that it's from your data set and has those characteristics, and if it doesn't, it doesn't. Actually, it turns out generative models can be fooled pretty easily, so it's not the best thing, but that's one of the kind of obvious, just theoretical application that you have.
So it's an attempt at learning the distribution of your data? Is that what you're saying?
Sorry, say it again.
Is this an attempt at learning the
Yeah,
distribution?
absolutely. This is absolutely, when I say the data likelihood, it's I'm using that in a Bayesian, sense, but I'm just saying you learn the distribution of your data. This is ways to do unsupervised learning, without some labels. So in general, that's the basic theoretical question. When we, the pixel RNNs and pixel CNNs, the VAEs, try to learn that likelihood distribution directly. I try to give you, your model is that distribution. These are a different approach, which is, well, what happens if we can, instead of trying to model explicitly, we model implicitly in the sense that we can sample from this. And so this is trying to do, something very similar to what we've been looking at before, but we're relaxing this condition and wondering what else, what do we get as a result? How are things different? One of the things that we can get in this kind of crazy way, there are other ways you can do this, but in this kind of crazy way of learning to sample from implicitly, is that we can get very sharp, very high resolution images, for instance. The way to think about that is if your data distribution has very many very steep peaked modes with no probability assigned to the configurations of pixels in between, that's very hard to learn, but these have a chance of doing that. There are the other problems like mode collapse that we briefly mentioned, but But that's like, that's how you do it. So, what are the applications besides just being able to sample from your data set? It turns out that like there's a lot of like really interesting ways in which this notion of like being able to create a thing that has these characteristics can like it can be used quite a bit. And we'll look at some of the applications. And some of you actually are like some of your projects are, trying to use GAN to do some of these things. But before we get there, just want to, here's like the basics of the basic training algorithm for like a deployment of GAN. Right, we're going to do a number of training iterations, and what we want to do for k steps, k being a parameter here, we want to sample n samples from our noise distribution. This is usually this Gaussian, this nice like isotropic Gaussian. Those are the things that we're going to feed into the generator that are going to give us images, the fake images, the generated images. Then we also want to sample the same number of samples from the actual data distribution. And then we want to use those to update our discriminator. Right, our discriminator has both these terms for the fake data, the generated data, and the real data. So we want to compute a gradient there, and we'll do gradient descent, stochastic gradient descent. Okay, so like that's for the discriminator, and then now we move over. Now we're going to train the generator. We're going to sample a different set, of M samples from our noise distribution, our Gaussian. We're going to feed those to the generator, and we're going to compute this, the gradient of this objective, and then do gradient descent here. And notice that this doesn't say for k steps. This is just one step. So this is like the typical way this is set up, where k is a parameter, and for a long time, using many steps, like more than one update step for the discriminator for every step we take to the generator was kind of the practice. Turns out that like other formulations of GANs sort of alleviate this kind of stability problem. This like stability here meaning that we by going back and forth between the discriminator and the generator, we don't just get like some kind of chaotic or like weird acyclic behavior in terms of how they converge, or like not converge in this case, but more get like some stable convergence to some appropriate loss for the data set. These sort of just like make it easier. Like you could just take one step and go back and forth. So anyways, this is the basic algorithm. It's actually pretty simple if you think about it. I mean, it's tricky in the sense that you got two models, but not really that big of a deal if you look at the pseudocode and just think, I'm just going to go back and forth between these. The reason why GANs are even around is that these samples are really end up being pretty awesome, pretty high resolution. And one interesting thing, I mentioned this interpolation in the latent space. You can do this with any model that has a latent space. You can do this with BAEs as well. You can like take samples from the latent space and generate the corresponding image, and like get a sense for like how the latent space is laid out. This is doing something like that. Pick 2 points in latent space, sample the line in between, and kind of see how you get this kind of smooth transition from one image to the other. But a really interesting observation that was made, and some of these generated images this is from like earlier work with these GANs, so not super amazing, but better than VAEs at the time. A little bit like hard to look at times. Is that you've got this kind of weird like emergent behavior in the latent space. So this is an example of this. So you take samples You take samples in your latent space that correspond to like some kind of characteristic. So for instance, like I might find that if I take a Z in my latent space and kind of sample around it, and we might find that like I'm generating like faces of smiling women in this case. I might do the same thing and find that I'm generating in a different part of space images of women who are neither smiling nor frowning, this sort of a neutral expression. I might do the same thing I might find another part of space where this is true for male faces, where again, not smiling, not frowning, just neutral. But what happens is, if I now do something like, okay, like this part of space, like just average all these, get some sort of like average representation of the smiling woman, latent representation. Do the same thing for each of these classes, and then do like some basic like semantic, like do some basic arithmetic that turns out to have some semantic meaning. So if I take this average representation of latent space for smiling woman, and I subtract from that neutral woman, with just being kind of silly and not thinking too hard about what's going on here, what I've left is the concept of smile, right? Like just like in a dumb way of doing this, like the difference between smiling woman and woman is that there's one is smiling and the other is not. So like the difference between there is smiling. Since I've subtracted this from this, like that's in the direction of smiling. And now I have a different part of latent space that have this kind of average representation of neutral man. And if I add this like concept of smiling to this concept of neutral man, what do you suppose happens?
Smiling man.
I set you all up for to give you the right answer. And indeed, it happens. It happens to be the case where, think about this. These are vectors in like some vector space, right? Like maybe it's 64 dimension, maybe 128, who knows? But I have this, I subtract from this, that vector kind of represents smiling. I add it to non-smiling, man. That gives me a new vector. And if I then use the GAN to produce the corresponding image to that, or like sample around it, you see what I get is like, the same style face here, but I get smiles. So I can somehow learn something about the semantic content here in doing this generation.
So what happens if you just keep going in that direction? Will the smile just get bigger and bigger until it's...
I don't know. Like usually what happens is because remember the latent space was learned as like a Gaussian, like an isotropic Gaussian over that vector space, right? So like usually centered at 0. So what usually happens is like if you move far away to like as you move far away, you're moving to regions of like lower and lower probability, right? Like that's what the idea of this distribution is, and so you start getting like images that don't really make they don't have like any kind of concept of like usually what happens is like this face will just get like really noisy. It'll be like a lot of noise overlaid on the face or something like that. So because it's a low probability, it no longer looks like what you want. But anyways, this doesn't always work, but it works so often. It's a fascinating kind of emergent concept here. You can keep going, like the same latent space, same model, same latent space. You have men with glasses, men without glasses. Get that average representation. Subtract glasses from non-glasses. So this is like kind of semantically, like this vector in that space kind of semantically represents glasses. I have this average representation of women without glasses, and if I add the concept glasses to it and decode that, or generate an image from it, I get something that looks like like this image, but with glasses put on top. So it's bizarre. It's really cool.
Is this the same thing that happens with like word embedding, like word embedding?
There's a similar kind of emergent behavior that happens.
Is the underlying
there
cause the same? Where you have a latent space?
No. Well, I mean, yes, in the sense that, like, the reason this happens is that there's that there are many examples of like, men with and without glasses, women with and without glasses, or like men smiling or not smiling, women not smiling, not smiling, and they share they share like the same generative factors. Like, you remember what the Z means, like what that space means. They're like, you think of them as each one as being like a factor, some reason for why the image looks, this way. So they're called factors typically, but it's like, each one of them is like an explanation for why the image looks that way. And the generator's job is basically to turn those explanations into like, the actual, image. And so the point is that because like smiling is basically the same whether you're a man or you're a woman, it's like we're using that concept across those classes. And so this, like the fact that like there's a vector. We could have done this differently, where like these were women, and that was a man, and gotten the same result, just that it's man with glasses. The reason for that is that like there really is meaning to adding glasses, like to this vector. So like in this space, it's most like parsimonious if a shift in this, like whatever direction this vector is pointing, corresponds to like adding the factor of like putting glasses on the face. And that happens also with the like word-to-vec, where there you have these n-grams, and you have like like the classic example there is something like, if you have, what is it like? It's like king. Wait, what does this go? King minus man plus woman gives you queen. Like it kind of decodes. I mean, the concept of decoding there is kind of funny, because it's just what you really do is you take that vector, like whatever the resulting vector is, you look for the nearest neighbors, and you find out like the vector corresponding to the word queen is nearest. Although it's actually super far away. Like the angle it banks with it is usually like 50 degrees or something, but still like these high-dimensional spaces, that's the closest thing. But it happens for the same reason, because like those n-grams of those words occur so many times that it's parsimonious, like meaning it's very efficient to learn like an kind of like offset, so to speak. In this case, in the case of word-to-vec, it's like an angles, but an offset that corresponds to that like similar concept that can be applied across various classes. So like, yes, there's similarity there, but the mechanism is pretty different in terms of how it's learned. Yeah.
Sorry, I might have missed this, but I don't understand how the GAN is like playing a role in this. I think I missed that.
Well, okay, so yeah, it's a little bit tricky. So corresponding to each one of these, remember that the generator is just a function from our noise distribution to our image distribution. It's just a function. It just takes it from one to the other. And so when I show you this, underlying each one of these is a vector in there's a vector in the latent space. So a vector is these are all generated images. Yeah. These are all generated images. Remember, like this is one of the things about GANs is that unlike the VAE, so a GAN only has a decoder, right? It doesn't have an encoder like the VAE. There are kind of ways to still like have a GAN concept and have both, but these plain vanilla GANs, they don't have an encoder. They only have a decoder. So everything you're seeing is a decoded image, or mapping us from the latent space to the image space. So when I show you these generated images, behind each one of these is a vector in latent space, a Z. And so like this corresponds to like the average of a bunch of Z's of male faces with glasses, a bunch of male faces without glasses, a bunch of women faces without glasses. Again, like you have to actually like sample randomly a bunch of points in space and decode and like see what you're actually getting. But yeah, you do all that, and then you start to like you have this average, maybe sample kind of close to here, and add these and add this vector, and that point in Z that Z in latent space that you're getting is decoding to these images, or generating these images. Does that make sense? Yeah. Okay.
I got a question.
Yeah.
Is there a way we can control the structure of the latent space so we know which direction this glass is and which direction is?
Yeah, like if you know these concepts like a priori, there are lots of, and this is true for the DEs as well, but there's lots of there's lots of techniques where you can impose that structure. Basically what you're doing is that you're requiring there to be like high mutual information between the concept and a feature in the latent space. Since you know a priori there should be something like that, you can actually build it in to be that way. Yeah. If you don't know, I mean, that's not necessarily. I mean, it's kind of it depends on how the approach is, but you start to kind of veer away from unsupervised learning at that point because you're starting to like take known concepts like labels and like shape the space that way. So it's not exactly supervised learning, but it does require some like a priori information to be able to do that. There are weaker ways to do this where you could like with MNIST, there are ways to like get like a class conditional generator without actually providing the classes, but just the knowledge that there are like 10 classes here that basically like learns to kind of cluster around the 10 major classes that just happen to correspond to the 10 digits, because like those have like the most distinction between just between the data sets. Like they tend to overly cluster with each other, is what I'm trying to say. And there's a lot of like research and ideas here, but in general, yes, the answer is you can shape it.
And a lot of these, they're generated with like 2D convolutions as all the layers.
Mm-hmm. Yep.
Are there any other layers besides 2D convolutions? It seems like 2D convolutions is like super good at representing faces and.
Yeah, I mean they're transpose convolutions, right? You're going from a vector to tensors, vector to the correct tensor size for the image. Yeah. It's just like what we've seen before. Yeah. These are all convolutional. Okay, so there were lots of GANs. I already pointed this out. Some of these examples out before. Like GANs have been progressively gotten better and better. Be able to produce sharper and sharper images. Some of the things that we've looked at from like the original papers and trying to do these things, 2014, 15, 16. You start going from 17, 18, and beyond. You just get just quite a bit of progress in terms of the ability to learn that data distribution, to learn those peaked modes around the precise configuration of pixels, as demonstrated here. And then kind of getting more at the types of things that you were asking, Kristen, earlier. GANs then started to be used to like transfer things like style and content from like one distribution to another. So there are a bunch of examples of this. So for example, I mentioned this last time. There's this thing called a cycle GAN. We're not going to get into the details of it. You can look up the paper, but the idea is that you basically have two generators this time. You have two distributions, like two image distributions, and two generators. One going from, taking the one image distribution as if it were like the latent noise distribution, and mapping it to this other distribution. One generator goes like that, and the other generator goes in the other direction. And so you have this kind of cycle where, like, if you take a sample from one distribution, map it with generator one to the other distribution, and map it back, that it really should be like an identity map when you compose those. It should take you back to what it is. And through this idea of a lot of related ideas, you can do this interesting thing where you can like transfer certain kinds of styles in the from one to the other. So this really cool example is this one of being able to transfer horse. So you have a bunch of distributions of horses and a bunch of distributions of, a bunch of images of horses, a bunch of images of zebras. These are two distinct distributions of images. You can learn like a cycle that maps you between them. And once you've learned to do that, you then take like a horse image, and you can send it through the horse to zebra generator, and you get the horses look like zebras. And then vice versa, you take pictures of zebras and you map it with the other generator from zebra to horse, and you get horses. You can do this for all kinds of different things. Here's another example from like apples to oranges and oranges back to apples. You can do this for different kinds of resolution. So like how you can, these kinds of concepts are used to like do super resolution. You know, like that famous thing in your, you know, crime investigation TV show where they hit enhance, you know, and like there's this totally blurry image, and all of a sudden like they can read the license plate, which is total garbage, right? But you know that now as, you know, physicists or whatever, engineers. But in general, you know, that's an impossible problem. But you can learn the statistics of that for a certain, you know, data set of like what it would mean to like super resolve things in the set, and you know, get really believable super resolutions. Not to read license plates, but whatever. And then like really totally interesting kinds of like things that you wouldn't maybe think of. You could take like you can transfer concepts like summer and winter in the same way. So like it's a little hard to see because it's smaller here, but here's a picture of Yosemite in the winter. You take this GAN that learns to transfer from winter to summer, and all of a sudden you have basically the same content, but now the style is of summer, and vice versa. And you can just keep doing this, and you can extend this beyond just these pairs of things. There's things called star GANs that allow you to kind of have a whole bunch of concepts that you can kind of transfer between. And you know, it's kind of fun that way. And then like and ultimately, remember like at the beginning of the course we talked about like deepfakes. Deepfakes use GANs to transfer the the style of a particular speaker onto another speaker, and that's how you get, you know, some of those deep fakes. You know, it's through using technology like GANs.
So it's GANs, but there are no VAEs that do this?
Typically not, because they just don't produce high enough resolution images. Now there are things called like VQ VAEs. And one of the groups actually is like thinking about, you know, using these. But these VQ VAEs they're vector quantization VAEs, and they basically what they do is they have like they learn code books that take you from like distinct codes to like distinct patches, and you kind of reconstruct your image from like basically like an array of integers, where each of those integers represents like you know, an exact configuration of pixels. So like you put images back together from a bunch of little patches, you know, obviously of like a whole bunch of different kinds to be able to get, you know, the kinds of variety of images that you can see. But you tend to be able to get really high resolution reconstructions that way, because each patch is already like high resolution, and that's quite cool. Like if you saw DALL-E from OpenAI like earlier this year, this was being able to do, you know, text to image synthesis. They didn't use VQ VAEs, but they used something very similar to it to actually do the image generation part.
It seems like VAEs and GANs, they kind of compete with one another, and it seems like GANs are winning almost.
It just depends on the application. I mean, lots of people still use VAEs for lots of things, but if what you need is like a high resolution image output, you typically would use a GAN or something like these VQ VAEs. There are reasons why you might choose one over the other that don't have to do with resolution, but anyway, there's lots of other applications we can talk about. This one right here of like a drawing of a bag and then turning it into a bag is like, you know, a concept, like an older concept called pix to pix, but it's this idea of like the customer could like sketch out like what they want, you know, like a bag, and then you can generate like from that sketch, you know, a believable looking bag, and maybe you make that kind of. There's all kinds of. Oh yeah, I forgot I had this.
Even the tail has stripes.
Yeah, there's definitely failure modes. You can see that the stripes are a little bit unstable in terms of like how they move about the body. But this is doing it frame by frame.
How come the whole background is also desaturated too?
Yeah, I mean, yeah. The nice thing with GANs is that if you don't like something about that, there's always a way to like, you can totally make it sharper. It's just really more of like the work that goes into getting it that way. Anyways, they really are amazing in terms of being able to especially for images, produce amazing samples from your distribution that seem really believable, seem to follow exactly, like they look like they're from the distribution. But they are pretty tricky to train, even though there's lots of techniques these days for how to stabilize that. They're still quite tricky. And in the end, you can't actually compute the probability or the likelihood of the data you just are sampling. Okay, so just moving along here. So we've been talking about VAEs, talking about GANs. There's like a lot of similarities. Can you combine them? And there are ways to combine them. Here's one of the more successful ways. This is called an adversarial autoencoder. So you have your autoencoder here, like what we had, like a standard autoencoder. We have our image, we have our encoder that takes us to our latent space, and we have our decoder that takes us back to the image space. And with the VAEs, you like supervise the shape of the latent space with that KL divergence term. Remember that? That's a distribution matching term, right? Like it's trying to, in the typical case, trying to make this latent space like follow like an isotropic Gaussian. Gaussian because it's simple, isotropic because you want your latent features to be independent of each other, and like the assumption is that if you can make it look like an isotropic Gaussian, then it would then like you hope that in the end that's what happens. It doesn't always happen, but at least it's pushing in that direction. Here, instead of shaping the latent space with that KL divergence term, you actually shape it with the generator. And what's nice about this is that instead of if you wanted there to be a different kind of distribution here rather than this Gaussian, this allows you to have really different kinds of distributions that to force your latent space to take on. One of the other reasons that you use Gaussians is that Gaussians and KL divergence give you really nice analytical terms. They're very easy to optimize. But if you want to do one of these other kind of like a really crazy distribution, again for similar reasons why you would use a GAN instead of a VAE to be able to sample from difficult distributions. If you do have something like that, then you can use these adversarial autoencoders to get the same kind of to get a crazy kind of distribution over here. And it uses a discriminator in the same way as you would use before, and just what happens is that you have like the idea of positive and negative examples, or just the idea that these correspond to samples from the actual distribution you want. These correspond to samples from your generated or fake ones, and you use your discriminator to tell the difference between them, and then you train your generator to match those up and so forth. So the idea here is just instead of in VAE just kind of always doing this KL divergence between a Gaussian and your latent space, this allows you to do far more interesting distributions and have a chance at learning those. So just kind of a fun variety here. You knew it had to happen, right? Someone had to smash these together and make a paper out of it. Let me just get through this.
Whoa.
What's kind of cool about the adversarial autoencoders is that you tend to get much nicer, sharper, because you're using Gaussians to learn the latent space, much sharper latent spaces, or transitions between the classes and things like that, which is kind of demonstrated here. MNIST jammed into a 2D Gaussian using variational autoencoders and using adversarial autoencoders. So notice how, in general, the classes are more together in the adversarial autoencoder latent space than variational coder. Same thing here. Instead of it, what we're learning here, or still learning MNIST, but instead of it being just like one single Gaussian, we have this kind of funny mixture of 10 Gaussians. And you would hope that, like, because there's 10 digits, that it would assign, it would assign each class to like one of those mixtures, but it doesn't do that. Any ideas why it doesn't do that?
Doesn't do what?
Like why? So remember, like this is the latent space. So it's trying to map, the MNIST digits into this 2D space. And our prior on here is no longer just a single 2D Gaussian, but it's like a mixture of these 10 2D Gaussians. And you kind of hope that it would map like all the zeros into one of these little, one of the Gaussians and all the ones in another one and so forth. It doesn't do that though. And why not?
Because these numbers have similarity between them.
Yeah, that's exactly it. That's great. So, if you just kind of look through like the color coding here,
It's like 9.
here are all our 2s, right? And then you can see that these are 9s. Here are some 0s. And if you think about it, like there's lots of 2s. There's 2s, and there's a lot of 2s that look like 9s and vice versa, and they kind of all live here, at this boundary. There's a lot of 2s that can look like a 0, depending on how poorly it's written. Those live at these boundaries. There's actually apparently kind of 2 different kinds of ways of doing that. And if you kind of go through the colors, you can kind of reason through what you'd expect to see in these parts of latent space. And if it did map these like zeros here, 1s here, 2s here, it would sort of say that there's there's something right here in the center of all of them that's like common amongst them all, which isn't the case for digit C.
So is the autoencoder acting as the adversary in this case?
Well, no, the autoencoder is the adversary in the sense that it's producing like fake. It's like the generator, right? It's producing the fake images, or like in this case, the fake latent variables, and then the actual like discriminator on that. So there's like a separate generator. So basically just think of it as like a discriminator that then looks at like actual samples from your latent space, but like the shape that you want it to be, like these crazy kind of mixture of 10 Gaussians, and whatever like the sample is coming from that you generated from your image, and it's saying the ones from your image are fake, the ones from this mixture are real, and the discriminator tries to tell the difference between them, and so this is why you get this really nice. And notice how not nice this is in terms of having matched the actual shape of 10 Gaussians. So it's just we haven't seen an example of this yet. We've always used images as a way of kind of visually being able to verify that we are getting sharper images, but here's an example where you just have this kind of abstract decision of what you'd like the latent space to look like, and the adversarial autoencoder is doing a much better job of being able to put you in that actual shape that you want. The variational autoencoders don't do that. And like truly, like here in the middle, it's a big mixture over all these modes. Cool. All right. You can have even more crazy examples. These are using labels as like conditioning, so you can actually, in this case, get your each one of those Gaussians to basically contain
Where's the adversary?
all the latents here. What's that?
Where's the adversary in this picture?
Well, this is a little bit different. You're conditioning this on a class, but this is generating fake, fake examples. This is learning to generate, these are just samples from the distribution you want, and this is just a discriminator saying, tell the difference between the two. So the generator is this thing up here. That's your encoder, and this is simply just samples from the actual latent space that you want.
Oh, okay, so gradient flows that way.
Yeah, the gradient flows through both of these, but yeah, it's shaping the generator to give you encodings that look like this distribution. And this just has an additional class conditioning on the discriminator, and it just allows you to do interesting things in latent space.
And then the decoder, does that see any gradients?
For reconstruction.
Oh.
I didn't mention this, but I still have the reconstruction loss to be able to. So in this case, remember this is like an expectation of P of X of Z, where Z was sampled from the encoder's distribution, just like how it is in the Yankees. So what you replaced is the KL divergence term that was trying to force the latent space to look like a Gaussian. You now replace it with basically like the discriminator loss that's trying to tell the difference, separating the difference between actual samples from the prior distribution and the ones you're generating from the encoder. These are cool. You can do lots of really cool things with them. I want to make sure we have enough time to go through the last part of this. Okay, contrastive learning. So yeah, this is kind of a basic concept. We haven't really talked about it yet. It will lead us into self-supervised contrastive learning, which is kind of hot right now, as I mentioned. But we need to kind of cover what contrastive learning is. So the basic idea, the basic way to motivate the idea of contrastive learning is that think about a classification problem where you have you have a whole bunch of images of actors. Obviously, we've got our most favorite actor, Brad Pitt, here, and all the different roles he's played over the years. And what you want to be able to do is say that we want an encoder to be able to look at all these and encode the Brad Pittness of all these near each other. We want to be able to when these things encode these images, that they basically they produce an encoding that is they're all near each other, because it's somehow just capturing the fact that there's a Brad Pitt in this image, but in this kind of metric way, in the sense of we want not necessarily that the classifier, there's a classifier that can tell this, but that these encodings are all near each other. And the reason why you might want to do this is for trying to solve the face recognition problem, where you want all pictures of a particular person, regardless of the location or the time in their life when the picture was taken. You want there to be a capturing of the essence of that face. And what makes that hard is not that that neural networks can't do this, but that if you're the government trying to surveil all your people, there's a lot of faces, and you may not know that they're all distinct. And you may not know you may not have a good label for all of them to begin with, and there's just a lot of labels, right? There's lots of people. And the classifiers will work for, maybe up to tens of thousands of labels, but they really start to fall apart when you have just too many labels. So is there another approach we can take where we still have some label information? We know that all these images came from Bill Gates or Brad Pitt or something like that, but that we don't train our algorithm to just simply classify and say that's Bill Gates or that's Brad Pitt, but to put images of the same person's face near each other, encode those images to give you late representations that are near each other. So like that's the motivation for this idea of contrastive learning. How does it work? Yeah, sorry, I was speaking through this and didn't let us answer these questions pedagogically here in the slides. If you have too many labels, the concept you want to have here is like everything from the same label should have an encoding or embedding that is close to each other, and then everything else should be far apart from it, far away from it. And the sort of like initial naive approach to this is what's been called Siamese networks. And the idea is that you're basically training one convolutional network. Okay, so like this picture here is showing some CNN, and this here is trying to say that they're the same CNN. They're using the same weights. Okay, so it's the same CNN. But I'm going to take two samples from the same class, right? Like two images of our most favorite actor, Brad Pitt, and we're going to use these convolutional networks to produce an embedding, right? So this is going to go to some kind of fully connected layer, not all the way through to a softmax layer. And then what we're going to do is we're going to take those two embeddings and we're going to literally say, okay, let's compute the difference between them, or the distance between them in our vector space. And we want to make that distance small because we want these embeddings for any pair of Brad Pitts to be pushed together. And so it's called Siamese networks because of the I think rather unfortunate connection to Siamese twins, but the fact that these two networks are really the same network kind of working together to push these things together. So this thing will learn to push the embeddings of these images together. How do we then do the other part of this, which is push different embeddings apart? Any thoughts? Oops. Any thoughts? So if we train this like this just directly right now, there could be some problems, right? Like, what's one solution that's going to make this absolutely perfect, perform perfectly on this simple metric of the distance between two images from the same class should be as small as possible? What happens if this network is just a constant function, right? Like it just maps any input to the same constant vector, like the 0. What happens then? This lot, yeah, go ahead, Chris.
Just bring similar images together, or similar images.
Yeah, so it's perfect. Like its loss is 0, right? These two things are the same constant vector. The difference here is 0. The lot, the magnitude of 0 is 0. So it's perfect, but this is not helpful, right? Like what we want is this other piece, which is if this is Brad Pitt and this is Bill Gates or any other actor, we want those embeddings to be different from each other.
So we want to add a regularization term, so you can make it so that if it's close to 0, or you can bump up the loss.
Yeah, you could do that. How would that give you a difference between two different images, but allow you to have, but still get a very small distance between two images of the same person? By doing that, you're going to move all pairs of images apart, not just the ones from different people.
So is there a KL convergence that we can probably do?
KL convergence. Yeah.
So this kind of pulls things together. We need something to push it apart, and
yeah, we need something to push it apart. So, How do we prevent this model from collapsing to a single point? So just learning to be a constant vector. I guess there are a couple different ways you could really do this, but what you want to do is you want to do what we were just doing when the pairs are from the same class, like the same person, they're images of the same person. But we want to have another loss that pushes them apart when the pair is from different people. And this is what's called a triplet network. And the idea here is that, again, we're going to use the same model, like they all have shared weights. So even though we're showing 3 different models here, the share between images, meaning they're actually really all the same model. And we're going to have, they go by some names. You have the anchor image. So Brad Pitt. You have a positive example, so another Brad Pitt, but different image. And then you have the negative example. Here's Angelina Jolie, and what you want to have happen here is that you're going to compute 3 embeddings off of the same network, and you're going to have a term that pushes the embeddings of these 2 images together and pushes the embeddings of these 2 images apart. And what do we mean by apart? Well, usually what we mean is like there's some margin by which we want to separate these images. And so you get what's known as a triplet loss. And it looks like this. For every triplet, again, the triplet being anchor, positive, negative, in this case, it's funny. Right? Here's anchor, positive, anchor, negative. This is anchor same, anchor difference. Got it from 2 different papers. But what you want to have is you want to have a term that is trying to push these. If we were to reduce this, make this as small as possible, it would be pushing these together. This term right here is non-negative, and it's smallest when these 2 things are the same. So that looks like the term you're just looking at for the Siamese network. And for the other pair, the anchor and the different, the anchor and the negative, we're going to compute the distance between them, but we're going to subtract that here in the loss. And so to make that as negative as, or to make that as small as possible, this is of course non-negative. Multiplying by -1 makes it non-positive. And so if we're trying to make that smaller, just increasing the difference between these 2, will give you smaller and smaller and smaller. We're allowing ourselves to get to negative values here, so that's what happens here. It's not quite the loss. You have 2 different other aspects of this. One is you have this alpha, or M, as we saw like in another slide, which is the margin. And so then what you have is this term right here, positive. Really, this is a max with 0. So the idea here is that you want all these terms together mean the following. You want this all gets zeroed out when the difference between the distance between the anchor and the positive is smaller than the distance between the anchor and the negative by a margin of alpha. So the loss in the end doesn't truly push these to 0 necessarily, but what it does is it tries to make the difference between these smaller than the difference between these by a margin of alpha. And what you do is you get a bunch of these triples. So like when you're sampling the mini batch, you have to pay. It's different than just like randomly sampling IID from the set. And to make these really efficient, you have to get quite good at sampling these efficiently, meaning like we produce like hard negative examples, meaning ones that that are still within this margin. And that can be a tricky thing to do, but in general, that's what you want to do. And you train this, and these models actually work quite well you can have a huge number of classes and be able to basically, take any images from the same class, map them really close together, and then take images from a different class and make sure that they're different from, they're further away by this margin alpha. So that's the triplet network. And this is called contrastive learning for exactly the reason that you have these contrasting examples in your loss. You have these similar examples, but then you have these contrastive examples that you're contrasting with. You're trying to push away. And remember, there's no like classification here, right? Like we go to an embedding layer, we go to some fully connected layer, and that's where our network stops. And that's what feeds into these loss functions here. We don't then go to like softmax and then go to like a cross entropy loss. We are literally working with the embeddings in the embedding space, trying to push similar ones together, different ones apart, and that's sometimes why it's called metric learning as well. Is that you have some metric, some distance function in your space, and you're using that to do the kind of pushing, putting together and pushing apart. Do you have a question?
Yeah. So is there like a bucket of like Brad Pitts and the buckets of someone?
Yeah, that's so like you still have all the labels, right? You might have all the faces. Yeah, you actually saw the news, like just last week, right? Facebook just said that they're no longer going to do face recognition. They're going to leave all the data that they used to do face recognition in the past and stop doing it. I don't know if you saw that. I'm not a Facebook user, so I was glad to hear that, but still don't use Facebook. But anyways, so they're stopping doing this, but essentially they were doing, for how like the 2 billion users on Facebook, whatever images they had posted of themselves and tagged themselves in it, they basically had this label set saying, here is an image of that person. You have 2 billion classes. You're not going to train a classifier to like recognize, that this, from a new image that person is, like which person it is. You would use a model like this to then, at inference time, what you do, you map this into, your embedding space and see which of the clusters of embeddings does that new embedding, most is it closest to. And then you'd say, oh, well, that's from, hey, there's another picture of Brad Pitt, or there's another picture of Angelina Jolie, or there's another picture of Anthony, or whatever.
This looks a lot like SVM loss.
Mm-hmm. Yeah, it is. Yeah, I'm glad you brought it up. It's basically the same thing, just you have triples here. But yeah, there's a mark. It's like a hinge margin loss. Yeah, we're running out of time, so there's lots of ways of doing these kinds of losses. We learned about softmax. I just showed you triplet. There are lots of ways of getting at like these kind of clustering losses. Center loss is another one. I'm not going to go through the details, but you're basically learning like a kind of, you're looking at kind of like representation of each class at the same time as you're learning representations from the class, and you're like pushing things towards it. There are really kind of fun, bizarre other kinds of losses that try to accentuate this. Sphere face, cos face, arc face are all kind of different ways of forcing images of the same class to be closer to each other. They do something slightly different from each other. Let's see if I can get to a slide just for lack of time. Yeah, that look like this. There's basically like different ways of thinking about this in the angle space where the margin that it's creating for the correct class and all the other classes, your softmax doesn't do that, but you can build in these margins into the angles made between things of different classes, and like for sphere face, this is just directly the angle, trying to push those apart. This cos face is pushing really the cosines of those angles apart, and this arc face is literally having like a linearly separable, what do you call that? margin between, in angular space between them. I don't really, need to like know the details. Just know that like there's a lot of different kinds of losses that are trying to do a better job of like forcing these things apart. And like the consequences are the following. Here is like embedding again MNIST into like a three-dimensional space using these different kinds of losses. And the point that you should be seeing here is that that the classes are being forced to cluster closer and closer together in the embedding space, with like more like stronger and stronger margins placed on different like parts of the loss. When there's no margins, you kind of learn to separate in this kind of smoothed out sort of like uniformly distributed Gaussian way. But as you start to have more and more stringent margins on the separation of the classes, you can see in arc phase, you can see how much more clustered these can be. So this is actually quite good if you want to do something like face recognition, because you need to jam a lot of things into your space. Like if you have a billion classes, you're going to jam a lot of things in space. You wouldn't use three-dimensional latent space, but you got to jam a lot of these into space. Oops. All right. Come back out, please. All right. Well, so contrastive self-supervised learning in 7 minutes. This is contrastive learning, but the difference here is that we're not going to be using labels anymore. Right? So like we were just looking at how you would use labels, like in triplet loss, you use labels to pick, for every anchor you can pick a positive example and a negative example. We're not going to do that here. We're going to do this in a self-supervised way, where each image itself is basically the positive example, and every other image is a negative example. And we're going to learn embeddings. So how we're going to do this is we're going to take patches of an image. We're going to take two patches of an image. Sometimes they might be overlapping, sometimes they may not be. And we're going to distort them through data augmentation. And then we're going to compute embeddings of those, and we're going to force those together. And then similar augmented patches from other images, even if they're from like a similar class or the same class, we're going to push apart using a kind of some notion of triple as well, and not do well. I'm always bad on so how to do these two things together? This is what I was just trying to say. So maybe this shows like tiling here just for simplicity, but you would take two patches from the same image. I thought that. Nope. I thought that. Shoot. I thought I had that video there. Something that was Here's the idea in a nutshell. So what you want to do is you want to take the patches from your image, and you want to augment them in two totally different ways. Like the heavier the augmentation in general, the better. And then that becomes your positive pair. And then you have, it could be still a picture of like an image of pigs, but a different picture. And then you'd augment it, and then that would become a negative pair with one of these two augmented images. And you train with like a triplet loss, or there are lots of different kinds of losses that are used, all with kind of a similar purpose of being able to compute similarity between the positive pairs and dissimilarity between the negative pairs. And you just train this way, and you produce these embeddings. And then what you do, once you have these embeddings, is that you do what's called like linear evaluation. You basically put like a simple linear layer on top of, like connected to these embeddings that you learn through self-supervision, self-supervised contrastive learning. And then you learn you learn a classifier, a very simple classifier, that goes, like for ImageNet that classifies the image as having, being from one of the 1,000 classes. And it turns out that you can do almost as well as in the supervised case. Okay. So what you're seeing are different. I'm not, just for lack of time, I'm not going to go through all the different kinds of self-supervised models that are out there. I have links to to papers and summaries on these things in the syllabus. But what I want you to see here is each one of these is a different type of self-supervised model, and it's showing you its number of parameters on the x-axis, and then its top one accuracy on ImageNet. SWAB is a kind of a self-supervised model here. This is just it's a SWAB getting bigger and bigger and bigger. And here is the green is state-of-the-art supervised classifiers. Their top one accuracy on ImageNet, and here's at the time the best self-supervised contrastive learning model. This is that linear evaluation. You can see for the same number of parameters, it's almost as good. It's not quite as good, but it's almost as good. So I know this has been really rushed, and I apologize, but just think about just try to take these 7 minutes and kind of summarize. What you've learned with self-supervised contrastive learning is without labels, you learn it in an embedding for an image that is solely supervised by itself, meaning that the positive examples in this kind of metric learning, this contrastive learning, are taken from the same image. And then the negative examples are taken from a different image, even if it's from the same class. And you do this kind of wild augmentation, and then this kind of metric loss, or this triplet loss, where you have the two augmented patches from the same image are pushed together, two augmented patches from different images are pushed apart. And if you now take those embeddings and you go and evaluate yourself on the test set for ImageNet, you learn a very simple single layer classifier from those. You almost get the same state-of-the-art accuracy, almost, not quite, but almost. Where, remember, this was trained specifically to do this task, specifically to recognize the correct class. Whereas we were trained to just put, different patches from the same image together, and different patches from different images, push them apart. And yet it contains almost as much information to be able to do this task, but was trained in totally unsupervised, self-supervised, but in unsupervised way. And this is really important because, in general, what you want to be able to do in deep learning is get away from having to use labels to get, to organize, some representation of images or audio or whatever it is, so that all of the right kind of content is there to be able to do any kind of downstream task, like recognizing what was in the image. And so it's quite impressive, right? I think this is one of those very recent kinds of innovation that is really surprising the deep learning just community in general. And the question is how far can this be pushed? And is this really a way to get toward get towards generally doing unsupervised learning? Supervised learning is still way more efficient when you have the right data for doing these tasks, and still the state of the art. But these things are becoming more general approaches to getting the same kind of information, and in the language examples, being able to be applied to a wider variety of similar tasks than just the specific tasks that these things are trained on. All right, so that takes us to 5. I'm sorry to kind of jam that into the end there. Sorry, I'll leave that up for a second to take a look at. But we're done for today. Happy to answer questions. If I gave feedback on your final project proposal you want to talk about, here, that happy to do that as well. But yeah, thanks everybody.
You also zeroed out all our scores too on
Yeah, but you got the one on the other one.
right? You got the score is being transferred over to the
It
other
hasn't been transferred over.
site.
Oh, it hasn't been transferred over yet, has it?
Yeah, it's, you have a one.